Okay, this is hello everyone. This is Jeff Z. Today, I'm going to share my learning experience of LeetCode problem 113. Actually, 113 Pass Sum 2. It is a medium level questions. Let's jump into the description. Given a binary tree and a sum, find out all the root to leaf paths where each path sum equal to the given sum. So this is a binary tree questions. Note, a leaf is a node with no children. Everybody knows that. Given the below binary tree, sum is 22. So the you need to return all the paths from the root to leaf if added up is 22. So I have another video talk about pass sum. The pass sum 2, the difference is it has to return all the pass, not only just one pass. Okay, so let's jump into my thought process. So this one is a first thing is we need to use the recursive for sure, and also it's a typical, very classic backtracking problem. So what you need to do is, if you find all the way, no matter if you find or not find anyone, if you uh, traverse from the root to the leaf node, and if you no matter if you find or not find um, the right path, uh, for if before you return back to the previous um, return back to the previous level, you need to remove a your current node so that it can actually traverse because it's a DFS. It's actually will do this. So the traverse will be like from this node to this node, then to this node, then to this node. If it exists, then it will basically add to the final result. If not, you need to remove this 7 from a kind of a temporary array, temporary list, and then go back to the upper level, and then add 2 into the temporary list. And if it is, then you need to add into the final result. If not, you still need to remove that, um, and then go to the upper level because there's it's already traversed the left and the right, so it will go to the even upper level and remove the 11 from the list. Same as here, it will remove from the 4. So you will understand what I mean here. So this is what I thought. The thought process I have is you need to keep an instance, do a backtracking, and the major thing of the backtracking is to remove the last element, no matter if you already find the path which added up to the summary, or you cannot find the answer. Also, another important thing is every time if you want to add a new list, don't forget to create a new instance. Uh, the reason is if you just add to you just added the temporary list, for example, from let's say from 5, 4, 11, 2 is the pass, and you directly add this to the result, final result, but at the same time you are actually modifying um, the temporary list, which gonna impact the final result as well because it's a reference. So make sure that you pay attention to this one. So let's jump into the code. You In this way I define the final list out of the um, out of the function as a class level variable, um, and this is the entry point of method. First thing is, if if the root is null, that means nothing will be returned. Sorry, there's no pass. In this case, we just return empty. Otherwise, I define a help function. So it's pretty much a DFS function with the backtracking. The first one is basically uh, the current node in the which is basically the root node. And the second is basically the remaining sum. Um, basically is yeah, so the remaining sum. And this next one is actually the temporary list that I mentioned. Is like you need to keep tracking um, which node should be added to the list. Okay, so again, that if the root is null, you return this. You just return directly because it's basically not even a leaf node, right? Um, and then you will add the current node into the list, which means that for if you start from the 5, you basically add 5 into the list, and then you will check, okay, if is the root left sorry, is the root left equals to null, the root right equals to null, and the root value equals to sum, which means that you find it's a leaf node, and also you find the final result, right? So then that means it's a candidate. Then you need to add your as I mentioned, this requires a new instance instead of adding the original list directly to the final result. You just add the result, which means you find it, and then you need to remove the last one, which is the leaf node, which is basically the leaf node that you added. In this case, it will be here, right? Which means that this root itself has to be removed uh, from the list, and then you return. So when you return, it's actually go back to the upper level, which is basically whomever calling this help function. Okay, so this is the leaf node situation. Then you'll actually go here, say, okay, I want to check the left side, right? Which say, okay, is the left side also has a, but you need to deduct the current uh, root value from the sum, and you will say, okay, in this case, we already add a root, right? So we'll say like the list including the root. What's the subtree? We want to traverse the subtree. Sorry, the left subtree. Um, see if there's anything that I can find, which is which is you know can add it up to the summary, the given summary. So which means that it's basically a DFS traverse from 5 to 4 to 11 to 7. And then it will say, okay, if everything is done, the left side is done, then we need to actually look into the right side. It's the same idea, right? Then after this is done, uh, you basically traverse all the way to the leaf node, and then after the leaf node is let's say if everything returned, let's say you hit the leaf node, and the leaf node, there's a left and right child, all no matter right or left child is null on the leaf node, right? Then it will basically return, um, and you're not able to find anything. Then you basically say, let's remove um, the leaf node itself, which means that it's going to remove this one, for example, and then go back to the upper level, and then add this one. And if it's and if it can find the result, it will actually uh, add it to the result and all the way to the and then return to the upper level. Um, so this is pretty much the algorithm, the backtracking algorithm. So the backtracking algorithm, um, there's one trick you always need to keep in mind is you need to remove one remove the last element. Lots of times it happens. You need to remove itself in order to get back to the upper level so that it can continue traverse. The time complexity I can see here is actually ON, and the space complexity um, is actually I think it's O. Um, it depends on. It's relying on how many levels this tree has. Let me check if there's any. Mm, so DFS with one linked list. Mm, yeah, so this is the same idea, but it didn't mention what's the space complexity. Um, okay. Sorry, time complexity is O in for sure, and the space complexity, I don't see any answer. So to me, it's the space I we need to define is need to have is pretty much the array list, and also you need to yeah, so you need to define this result, which is I think it's also in. Yeah. So in this case, yeah, so the time complexity and space complexity um, is both ON. Um, I'm not sure if I explained this well, um, but this is my learning experience. It may not be the best explanation, um, but I hope this will help you to understand, um, the the lead code problem. Thanks everyone. See you next time. Thanks for watching. Bye.